All right. Thank you very much for inviting me here. Actually, you should blame Marco Arena because I always want to, I want to quit C++ and go to Haskell and do category theory, but he always invites me back to C++, so I have to like write some C++ code so that I can show some. Okay, I'll be returning to C++ from time to time. My goal here is to make make the word monad acceptable to C++ programmers. It used to be many years ago that monad was a dirty word, you know, you were not supposed to say it in public. But eventually this changed, and like I went to several C++ conferences where actually people, after my talk, people would come and ask me questions about monads and so on. So this is a very important topic, and it's a mysterious thing, right? The monad. It's like there are people who get it, and there are people who don't get it, and it's like, once you get it, it's like, oh, wow, you know, there's this feeling, I have to write a tutorial immediately, right? I've been through this too, right? But the more I learned about monads, the more I understood, the simpler it became, you know? It's like, and now I see that it shouldn't be that hard to explain. Right, and I will talk mostly about one monad that's like the most mysterious monad, the I/O monad. Right, the I/O monad is something that people don't even mention in C++, maybe because it's not very useful, but it's a very weird monad because it deals with input-output in a functional way where you have pure functions. So this is like a contradiction in terms, and how can you do this, right? So let me start by telling you why monads might be interesting. And to introduce this, you know, the monads are about composition. And I cannot stress enough, I have to repeat this thing, the programming is about composition. Everything we do is about composition. And in fact, everything we do in real life, in science and everything, is always about composition because we cannot deal with complexity in other ways other than if we can decompose it into smaller pieces and digest them separately, right? And then recompose them in bigger things. So monad is this is why monad is such an important pattern, because it lets us compose things. That's the main reason. So in what sense programming is about composition? Well, of course, when you build data types, for instance, obviously you compose more complex data types from simpler data types, right? Everybody knows that, right? When you write code, the code that executes, right, you are dealing with function composition. And this is something that for C++ programmers is not immediately obvious because you don't really see it in your syntax, right? But think this way, you know, like when you are implementing a function, right, you probably call one function after another inside this function. There's some code that glues functions together, right? And like the simplest way of composing functions is, well, you call a function with some arguments. It gives you some value in return. What do you do with this value? You call another function with this value, and it produces some other value, right? So this is, in a nutshell, function composition. Like in Haskell, you can actually, you have an operator dot. You say this function composed with this function, composed with third function, and you know, in C++, you don't even have it in the library. I don't think there is a compose template that can compose functions. Or maybe there is, huh? I haven't. There is? Okay. I'll trust you. on that. It's probably like 7 pages long, right? Well, it is difficult in C++ because there are so many ways of passing arguments, right? You can pass by value, by reference, by pointer, by move, semantics, and so on. So yeah, this is really complicated, and depends what you want to do with this argument. Do you want to forget about it, and so on. Do you want to deallocate it afterwards, maybe, you know? So normally, also in Haskell, I mean, this is called point-free programming when you just chain functions one after another, right? So they got pipelining the functions. Do this, do this, do this, do this. And you're passing data through like a pipeline, right? Even in Haskell, we don't do that much because it's not very readable code. What we usually want to do is have these intermediate values that have names, right? So this is a good thing and a bad thing. Like a bad thing because you have to come up with meaningful names, right? And sometimes you run out of ideas. On the other hand, you know, if you put meaningful names, then it's easier to maybe read your code and understand. So the standard pattern of function composition is you call a function, you assign its results to some variable that you name, right? And then you pass this variable to another function, right? And of course, there are combinations. There is inline code, like when you multiply two numbers, it's really a call to a inline call to a function multiply, right? So there's a lot of invisible kind of, but it's all lambda calculus at the bottom, right? So if you think of code as composition of functions, then there's this very important thing that you can do. You can say functions take arguments of some types and return arguments of some other types. What's the use of this? Well, you have a type checker, right? So strong typing is like the most successful program verification technology in existence, right? I mean, I don't have to convince you C++ programmers that this is good, having strong types, right? But when you talk to JavaScript programmers or, you know, other untyped language programmers, you know, just ask them this question, you know, like if I give you a verification tool, you know, that can verify the correctness of your program, at least to some extent, right? Why would you throw it away, right? I mean, this is such a great technology. It just checks types, you know, whether you are plugging your Lego blocks, the functions, correctly or incorrectly, and that's it, you know? It's like, please use that, right? So in a purely functional language, you know, function composition is very easy because you just look at what the input type is of a function. So I'll call it with an argument of this type. What's the output type? Okay. So I have the output type. I can call the next function that accepts this output type as its input, and I'm done, right? So it's this end-to-end type checking. Excellent, right? And of course, I don't know what this function is doing, but I know that it calculates this type of output from this type of input. Now, if you have several functions that are called, and the input of one depends on the output of another, right? That's called data dependency, right? So if you have this kind of data dependency, the compiler knows, and you know, and everybody knows, that you first have to execute this function that produces the input to the next function, right? Obviously, right? You cannot say, okay, I'm going to first execute the second function, right? No, you can't because you don't have the input for it. Okay, so when you have data dependency, you cannot invert or run in parallel these functions, right? And in a purely functional language, if you have two functions that have no data dependency, like the output of one is not the input of another, then you're free to invert the order of execution, really. Or you can run them in parallel if you want, right? There's no reason not to do that. And this is where this you know, so if in functional languages, functions are the pure functions. Pure functions are the ones that have no side effects. A pure function, when you, first of all, when you call it with the same argument for the second time, it will give you the same result, right? So it always produces the same result for the same input. But also it produces no side effects. It doesn't do something on the side that it's not telling you, right? Everything the function does, it's kind of telling you in its signature. I'm taking this type of arguments and I'm producing this type of value. Now, if you have functions that have side effects, for instance, they interact, and one of the side effects is interaction with the external world, like asking the user for input, or printing a string, or reading a file, right? Or moving an arm of a robot, right? These are side effects. If functions have side effects, even if you have a function of void that returns void, and it moves the arm of a robot or prints a string, you cannot change the order of execution of functions that do this, because that would result in weird behavior, right? So suddenly there are these hidden things, and they break this beautiful compositional property. And one role that monads play is to make these side effects again composable. Okay, so you can regain the compositionality of your functions if you are using monads, and I'll show you the example. And the I/O monad is the most difficult one to understand because you know, it deals with interaction with the real world, right? So when you are interacting with the real world, that's side effect. How can you get rid of a side effect? How can you describe using pure functions things that have real world side effects? So that's what I'm going to talk about in the beginning, right? So here's an example of a program in which this illustrated, right? So we want to write a program that first asks the user for name, so it prints what's your name, and then calls getLine. This is pseudo syntax, right? Gets a name and then prints hi name, right? Simple thing. And notice that there is no data dependency between line 1 and line 2. The line 2 does not use the result of line 1 because print, I don't know, printf returns some error code which is always ignored or something like that, right? So nobody cares. There is no data dependency. A compiler should be able to switch these two lines. Like, what happens if you switch these two lines, right? The user will not be prompted, and they will not know that they have to type their name, right? So that doesn't work, right? And I was thinking of, you know, how can I convince you that actually an I/O monad might be useful in C++? And really, it's really hard, right? But there is one example in which controlling side effects is extremely important, and that's in software transactional memory. So if C++ ever gets STM, then it will have to deal with I/O, right? And probably the way if history is repeating itself, it will deal by telling the programmers, don't do that, okay? Don't do I/O inside a transaction, right? Because everything will break. Why? Because in transactional memory, what happens is you start a transaction, right? You execute code that does some modifications of some variables and so on that are shared between threads, right? And then if some other thread steps on the variables that you modified, then one of them will abort, okay? And what happens at this point, you have to undo everything you did and start from scratch, okay? So most operations, like writing to memory, are undoable. If you remember what was there before, you can like replace it and so on. Like you unwind your transaction, right? If you keep a log what you did, well, you can undo it. Right, but if one of your instructions is I/O, and let's say it sends missiles and explodes a bomb or something, or just prints to screen, you cannot undo it, right? So controlling side effects, and especially controlling I/O, in this case, might be extremely important. So if you want to do I/O inside your transaction, you will have to use some kind of trick, right? And one of these tricks is using a monad. I mean, the other trick will be, I'm just logging something to a string, and then after I end the transaction, I will print the string or something like that, right? But this is like the most general way of dealing with side effects. So I'm going to show you now some code, okay? And the I/O monad is really very simple to explain in terms of implementation. Because what we want to do is, instead of performing the I/O at a given point in time, we want to suspend it. We want to say, okay, at a later time, perform I/O. Right? Not right now, because I'm in the middle of something, okay? I'm in the middle of a transaction, right? So don't do I/O right now. But remember, at some point later, to do the I/O, okay? So you want to have something that's like an I/O action, okay? So this is a simple class that just remembers what to do. Right? So this is called the I/O action. And it's sort of, the idea is sort of like with futures. It's like you perform some calculation and it gives you back a future. Right? This future does not really usually contain the value. Right? This value will appear maybe later. Here, this is like the extreme thing. You get a future sort of, but it does not contain the value. It will actually not even start executing it. It will only execute it when you call run, right? So you have to call run at some point, and then it will execute. So suspending something means just remembering a function that will do this. So usually, you can give it a pointer to a function. You can give it a lambda, right? A function object, anything that's callable. So this class T is, in the future when we have concepts, this will be a callable concept, right? So here I'm just, T is the return type of the function, right? So I'm calling it with a standard function, and if I call it with a lambda or something, it will be converted to a standard function, and I'm storing it. It probably could be done, more efficient if I just make it the whole. I guess I could do the whole function as a template parameter, right? Yeah, but this is like more in the spirit of what we do in Haskell. Okay, in Haskell we have this type called I/O. This is a type constructor because it takes another type and creates this I/O for this type. Okay, so the way to understand this is an action that will produce a T eventually. How do you get this T? You have to run it. When you run it, you'll get the T. Okay, so we are storing the standard function as an action right? And we have run. We'll add some more methods to it, okay? But this is a primitive. Now we want to create a vocabulary that uses this I/O. Okay, so we want to create some functions that return I/O, that return I/O actions. So I/O action itself takes no arguments, right? But we want to create functions that take some arguments and produce I/O actions. So this will be our vocabulary. We have to have some basic functions that do useful stuff. For instance, put string. Put string will just print a string. Well, not really. It will not print the string immediately, right? It will create an I/O action using this lambda here that captures the string, right? And later on will send the string to standard out. And you might be asking, what is this U they're doing? Okay, so I'm using this U as a unit type. So this is, in Haskell, we have unit type. And unfortunately, in C++, you know, C++ is like a stack of special cases. So whenever you have a template that's templatized on some type, you know, you probably have to specialize it for when T is void, right? What if you have a function that returns a void? Well, this function returns a void, right? It's printing something, so it's not producing any output, right? There are functions that take void because they don't need an argument, right? So if you want all your functions to be sort of uniform and takes an argument, returns a value of some other type, and you don't want to special case for void, that's the trick you use. So everywhere you have void in C++, you could replace it with this unit. I mean, this is something that probably the C++ standard should do and just make void a regular type rather than this special symbol for, you know, I don't really care about my argument, okay? Okay, so this is one function. And this is the other function that's very useful, getLine, okay? Now, getLine is like the opposite. It takes U. It does not need any argument, so it takes a unit, right? That's void, right? But it produces a string. So, well, it cannot produce a string because it needs the user to type in the string, right? So it cannot produce a string. But it can produce an action that contains a string. Okay, so it's like, think of future that returns a string, right? In this case, it's not a future. It's just a function. See, so it initializes the I/O to this lambda, which we'll call getLine, put the result in the string, and return this string. So this is the action. When you run this action, you'll get a string. Okay? But when you call getLine, you don't do any. This is a pure function. Okay? You don't do any input-output when you call this function. So these are pure functions. Okay? So if you need pure code, you can use these functions freely. You can use these functions inside of your transaction. Okay? Just don't call run. Call run when you're done with transaction, right? Now, what happens in Haskell, for instance, is that you cannot run an I/O action at all. You're forbidden to do this because it's a pure language. What happens is your whole program produces one gigantic I/O action, okay? And main returns this I/O action. Okay, actually main is the I/O action that you are constructing, right? And then the runtime calls this run and executes, okay? So that's a clever trick that's done in Haskell. But Haskell is a lazy language, so this is possible. But in C++, you know, I mean, you can kind of like get a around this by saying, please don't call run until you are sure that it's okay, right? And then it will be fine. Okay? So these are two functions. Like, are we going to provide functions for every possible action that we can think of? You know, it's like, what about this third action that produces a string, hello, comma, string that's an argument? Okay, do we have to like write yet another function for that? Or can we compose, okay? And that's the trick, right? We want to be able to take functions like these and compose them. And this is where the magic of monad happens. Monad says, let's compose these functions, okay? These functions are not normally, in the normal sense, composable, because look what happens. The input and output don't match. The output of this one is IO of U. The input of this is U. I cannot call getLine with the, or after running put string. The arguments don't match, right? This is bare U, and this is IO of U. So I have to be able to combine them, but I have to put some glue in between, right? There needs to be some special glue, special ingredient. And this glue is called bind. And let me illustrate how this is done, okay? So the naive way of doing this, if we were like not postponing stuff, right? So we have this function put string, right? Put string takes a string as what's your name and produces an action, IO action of type U, unit, void, really, right? If we want to combine it with the next function requires a U. How can we get a U? Well, we have to run it, right? Okay, so naively speaking, we would run it, then we would get a U, and we could pass this U to getLine, right? And getLine would return us an action that returns a string, okay? Okay, now we want to call this third put string, right? But we need a string from this one, okay? So how do we do this? We would have to run it, right? So we run it, we get a string, and then we put this string and return U. We create this IO action, right? That does this. And then finally, yeah, we run this action, and it actually outputs the string and produces a U, and we are done, right? So this is really not what we want, right? No, we don't want to run these things immediately in order to combine them. And it must seem like such an obviously wrong thing, but this is how futures were designed, okay? Futures were designed in this way. Like every time you want to pass the result of one future to another future, you have to wait, right? You have to block. So the lesson that should be learned, you know, from the bad design of futures, this is being fixed now. It's like in experimental, you know, there is a bind for futures, and there is, I'll show you in a moment what is needed to make it fully into a monad. But it's like for somebody who knows what a monad is, it's pretty obvious that a future must be a monad, right? So what is the trick? The trick is that we want to take this part here, right, and encapsulate it, abstract it, okay? So instead of running this IOU that we are getting from the first put string, we want to create a new, bigger action, okay? So I'm just like showing you this is the bigger action. So you don't want to execute the run right here, but you want to say, I'm constructing a bigger action. And when you call run on this bigger action, then I will call run on this IOU that you gave me. I'll just remember it, right, the IOU. I'll run it. I'll get the result. I'll pass this result to the next function, run it again, right? I mean, call this function, and we'll produce an IO. And I have a bigger action, which takes a string on this end and produces an IO action that produces a string on this end. So all this stuff will become one big action. And I'll show you the code. The code is reasonably simple, and it just follows this picture, right? Except for the, type inference in C++, which is not that automatic. So this is a function bind. It's a template bind, right? And it's a method of I/O. So it has access to this previous action. Okay, so there is this previous action that I don't want to execute, right? However, I want to create a new action. So this is why I'm doing this return IO decal type, blah, blah, blah. I'll explain in a moment what type I have to put in there. But I'm creating this new lambda that combines all these things that were in the box. So this lambda will actually call the action, right? It will call the action, will get the result, pass this result to f. F is the parameter there, right? It's a callable thing. And then f itself produces a new action. So I will run this action. Okay? So if you go back to this, stuff, okay? This stuff. This is a member of IO of you in this case. So this is my this pointer. I promise that I will eventually run it. So I'm creating this action that will run it, pass the argument to the next function. This is the function argument, this f, the big F, the f, right? And we'll produce a new action that I will run. So actually, I think this box should also include the run in this case, right? Okay. So here's a test program, okay? It actually works, okay? So I'm calling putStir, passing it a string. So putStir produces an IO action of you, IO of you, right? This IO of you, I can bind, I can call its method bind with getLine. GetLine is a function, right? It's a function that returns an action. So it fits the pattern, okay? So I call bind with this function, and it will, these two lines together will generate a bigger action that does both things. So I was able to compose these things without actually running it, okay? I have not run any I/O, but I have composed these two actions into one bigger action. And this bigger action, I can call bind as a method of this bigger action, right? And pass it a lambda. This lambda takes a string, because this thing produces an action that returns a string, right? I don't have a string yet, but I can call bind and say, later on, create an action that will run this whole thing, give you a string, and this string will be passed to my lambda. And then I can print this, okay? So this is complex code to do a simple thing, right? But it has this very nice thing that it does not do any I/O. This test is a pure function. It doesn't do any I/O, right? It returns an I/O action that is a combination or composition of these three different functions. So I was able to compose these functions in such a way that I did not run any I/O. After I'm done with this, I can take this object and I can say run, and it will do all three things. Okay? So it will actually do what I expect it to do. Right? I'm calling test. It returns an I/O action, IOU, right? And I call run. And that's print. What's your name? I type in my name, and it prints hello, my name. Okay? So that works. Okay, so this is the, so a monad consists of three things. Okay? One is bind. You have to be able to take the result of one function that, or take one action and bind it to a function that returns another action. Okay? This is a simpler thing. fmap is okay, so I have an action that is supposed to produce some type t. I want to modify this type by applying a function to it, right? And it's just a regular function. It's not a function that has side effects or anything, just a regular function, right? But I cannot do it immediately because I don't have the value yet, right? In order to have the value, I would have to run my action. And I don't want to run my action because it does nasty things, right? I want to postpone it. So I'm creating a new action that when the time comes, when it's safe, it will run my action and apply the function to it. Okay? The difference between fmap and bind is that fmap just applies a regular function, not a function that produces I/O action. Okay? So the example of this is you know, uppercase, right? So I have rewritten this test to get line and then uppercase it. Okay? Uppercase is a pure function. Well, in this case, yeah. I mean, it just produces a new string that does the uppercase. That's uppercase of its argument. Right? And of course, this uppercase will not happen here because there is no line yet from the user. It will happen later when I run this I/O action. When I run this I/O action, these things will happen, and the fmap will happen, and uppercasing will happen, and so on. And the string that's displayed will be uppercased. Okay? Clear so far? Okay? This is sort of like if you know what futures are, you know, just imagine, okay, I'm starting a thread, but I'm not really starting a thread. I sort of like using packaged task instead of starting a thread, right? So I'm postponing the execution forever until somebody calls run finally, right? So the third part of a monad, so bind, fmap, and the third part is, we call it return in Haskell, but you can call it pure. It's also called pure when it's applicative, but you know. So this is a function that's useful because it takes a value that's available right now, immediately. Okay, I don't have to wait. I don't have to do anything. I have this value, right? But I want to return an I/O action. You'll see in a moment why you want to return an I/O action, because you might have a function that like figures out, oh, do I have to like make more input output, or can I just return a value, right? So at the point at which it decides I want to return a value, but it's a function that is possibly doing I/O, so it has to return an I/O action. So it just encapsulates this value inside an I/O action. Just creates a very simple lambda that just returns this value. But not now, I'll return later. Right? Remember this value and return it later. Okay? So here's an example that shows you that this I/O monad can be used in a more complex task. This is a guessing game in which you pick a number between 1 and 10, for instance, right? And the computer says, is this less than 5 or greater than 5, right? And just binary search and guesses the number that you've had, okay? So immediately you have this forking, right? There is an if statement. So guess takes this range. This is between A and B already. I know it's between A and B. But, eventually A will be equal to B, right? And when A is equal to B, or A greater than equal to B, just to be on the safe side, right? Then you want to return this value A. I'm done, right? But this is a function that returns an IO of int. So I have to encapsulate it using pure as a very simple IO action that just returns this value, right? It does not do any input-output because it's done, right? So this is how pure is used, okay? Otherwise, if I have to continue guessing, okay, I will take this range, like chop it in half, right? Find the middle point, and I will ask the user, is this less than m? And this function ask, since it does I/O, right, will return an I/O action. Well, it doesn't do I/O at this point, but it returns an action that will be done later, right? So it returns an action that asks the user, is this greater than m, right? And this is a Boolean action. It has a value of bool hidden there, right? It's a future of bool. So I can bind it to a function that takes a bool, right? And does an if statement. If this is less than m, then let's use the left subrange. Otherwise, use the right subrange recursively to just keep asking, keep asking, keep asking. And you see what happens is it's like you are creating one gigantic I/O action. Nothing happened yet. You're creating recursively this one gigantic action, and the depth of this action depends on what the user will say, right? So it's dynamically done. It's like the user will answer these questions eventually, and this will terminate. But you have this one gigantic action that is recursive in itself. And this is the implementation of ask. And I used this pipe operator. I overloaded it to do bind. So this kind of better syntax for it. So we put string, then we call put number. Yeah, is it less than? Put number, yes or no, get line, yeah, check it against yes, and so on. So this is sort of straightforward programming here, right? The syntax is not very nice, but, well, it's reasonable, right? So the thing with the syntax of this, okay, let me have a little digression. It would be a problem also in Haskell doing binds inline, right? This is a staggering number of binds done one after another. This is kind of ugly. So Haskell came up with this notation called the do notation, in which you don't have to. So you just sort of write it like as if it were imperative code, okay? So in this respect, Haskell just like tries to look like imperative code, and because it's easier to understand in this case when you have side effects. In C++, there is a proposal for something similar called coroutines, okay? Coroutines actually correspond to Haskell do notation. And I really hope that coroutines will be done right, in the sense that they will work for any monad. Right now, well, the first idea for coroutines was, let's do coroutines for the future monad, right? To do asynchronous stuff, because this is the same thing, you know. I mean, very similar. But then they realized that, you know, you can do it for more things. Like you can have generators in coroutines, right? But really, coroutines should be used for any monad. And in particular, there should be a way for a user-defined monad for users to define their own monads and use coroutines for them. It would simplify the syntax tremendously. Okay? All right. So how much time do I have? Can I? 10 minutes? Okay, so let's do 2 more monads. Okay, 5 minutes per monad. Okay, so just not to give you the wrong impression that monads are all about I/O, because this is what happens with everybody. Okay, they learn about one monad and say, oh, now I understand what a monad is. Monad is all about side effects and I/O, right? Okay, now it's like with these blind people who are touching an elephant, right? Oh, this is like a trunk of a tree, right? This is like a snake. No, because there are so many different monads, and each of them is completely different. But they have this one common aspect, that they are all about composing things in interesting ways. So you always have this way of, okay, I have functions that don't return like naked values. They return values in some peculiar way. For instance, they return functions that will produce these values. Or they return something else that kind of contains this value, but you have to do something to get this value, right? And one way of doing this is you call this function, it returns this something, and you do something, you get the value, and then you call the next function with this value, and so on. But as I showed you, bind is the abstraction of do something to extract the value and push it to the next function, right? So this is what bind is. So let's implement bind for something else. Okay, and this is, I call it option, but I think this is called optional in C++, and it's probably not going to be implemented as a monad. Again, a mistake, right? So an option is, in general, this is, theoretically, this is about a computation that can fail, okay? So you have some computation that is okay for some, like square root, right? Square root is only works for positive numbers, unless you use complex numbers, right? But let's say positive numbers, right? Non-negative numbers. But for negative numbers, it's not defined, right? So this is not a pure function. A pure function in functional language is a total function, right? It has to have a value for every possible input. This one doesn't. Okay, so what do you do? So normally you would use exceptions in C++, right? But if you don't want to use exceptions, for instance, you are not allowed to use exceptions because you work for a company that bans exceptions, right? Then what's the other option? The other option is use option, right? So you just say, okay, I will encapsulate my value into something, some object called option, that either contains this value or says error, right? Or like I couldn't, right? So it's empty. So again, this is something that has a value or not. Just like the previous one, it sort of has a value, but not immediately. I will give you this value later. Right? This one says, I maybe have a value, maybe not. Like in Haskell, it's called a maybe, you know. So option here has this is like not very efficient implementation, but bear with me, right? So I'll put a Boolean valid, which can be true or false. If it's valid, then I have a value of type t. Okay? So just like before I had I/O of t, here I have option of t. There's always this type constructor going on. You know, like I'm hiding a value of type t. Maybe I'm hiding it, or maybe I'm not. Maybe it's invalid, right? So it has two constructors. One of them sets value to false and no value, and the other sets it to true and inserts the value, right? So how do you do bind? Well, you have to check whether I am valid or not. If I'm valid, then I can call the function f, the continuation, right? The next function in the chain of command, right? With my value, and it's okay. If I don't have this value, I'm not going to call it at all, right? This is called short-circuiting, right? So normally when you would write code like this without option, you would say, call this function. If it returns a value, then call the next function, else do something, don't call the function, right? Here you encapsulate this logic of checking the previous value inside bind. So you are guaranteed that you will have a check done. And you will never call a function if the previous function returned invalid value, okay? So for every monad, you have to have bind. You have to have fmap. Fmap does a very similar thing, right? And you have to have pure, right? So pure just takes a value and puts it into an option that's valid, right? This is a valid option, right? And here's a short example, like optional square root, right? So it returns optional double. If it's greater, if argument is greater than 0, then return pure square root of x, right? You do the square root because you know it's not negative, so you can do it safely. You return it, okay? So this is like your atomic basing. But if it's less than 0, then just return option, empty option, meaning invalid, okay? Here's the inverse. Similarly, if it's different from 0, then you can invert it. Otherwise, return an empty option, right? And then you can bind one after another, and you don't have to do any checking because the checking is done inside bind, right? So you do op square root of -1, okay? This will return invalid. You fmap double multiply by 2, but fmap will check this result and say, no, I'm not doing anything, okay? And then you bind it to inverse, and the inverse will try to do this and say, but this guy returned nothing, so I'm not doing it anyway. So you short circuit everything, and you return, well, y will be an invalid option in that case, right? At some point later, you check it. And this works exactly like exceptions, right? If any of these guys fails, it bypasses the other guys. Right? This is like just like exception does. And at the end, you do a catch exception. In this case, you will take y and say, are you valid? If I'm valid, then fine. If not, then do something else. Okay? And just to throw you off completely, I'll show you that a vector is a monad as well. Okay? So a vector monad, this in Haskell it's called a list monad, but you can do it for vectors. It corresponds to a computation that returns multiple values. Okay? And normally when you combine things that can return multiple values, you will say, okay, so the first function returned like 100 values, right? And I want to apply a second function that also returns, like, let's say, 10 values, right? I have to apply it to every element that was returned, right? So that corresponds to a nested loop. So bind in this case, in the case of vectors, actually corresponds to nested loops. You can do nested loops using bind, right? So here's the bind. It actually does a for loop, right? And goes over the first vector, this vector, right? Gets all these values, right? And then calls the function f, and the function f again multiplies them, spreads them into a new vector. So for every value that I got, I have a new vector, like a fan out, right? And I just combine all of them in one huge vector. So that's the implementation of bind. The implementation of fmap is use a standard transform. You just apply the function to every element, right? And the implementation of pure returns a vector that has just one element. Okay, so it takes a value and puts it in a vector, but it's a trivial vector of one element. Okay? And here's the example how to use it. So I have this function triple that returns a vector of 3 elements. I have a square because I want to apply, yeah. And here's a little program. So I take a vector, v, right? I fmap square over it. So I square every element here. And then I bind it to triple. So for every squared element, I will produce I minus 1, I, and I plus 1. And we'll create this longer list. Now, this is not a very useful example, but just shows you how this works. OK, I'm almost done. So to summarize, actually, right? Almost done, yeah. So the way this pattern works, like if you want to remember what the pattern is. So the pattern is you have these functions that are called monadic functions. These are functions that take some argument, whatever argument of type t, and they return this monadic encapsulation of the value. So it's either IO or option or a vector, right? So the whole thing is I have functions, these monadic functions of this type, and I want to compose them. And you compose them using bind. And bind, as a freestanding function, it can be a method or a freestanding function. It takes a monadic value, right, and takes a function that takes a value, not the monadic value, but the t itself. It's a function that takes a t itself, but returns a monad, OK? So I'm staggering these things using bind, right? And then there is fmap that just simply applies a function to whatever is inside my monad, right? And finally, there is this pure function that just takes a value and embellishes it as a monadic value. Okay, and finally, I have to say something, don't use this in production code, because otherwise the heckler here will heckle me, right? Yeah, I talked about it with Edward Kmed, and he said, if you don't tell them not to use this, I will heckle you, right? Because there is this big problem, right? I mean, it works very nicely until you start binding very deeply, right? If you do an arbitrary number of binds, you will blow your stack because it's a function calling function calling function calling function calling function, right? Why this works in Haskell? It works in Haskell because we have tail call optimization, okay? These are tail calls. And the compiler just converts these tail calls into loops, okay? But you have to have arbitrary tail call optimization, something that Scala doesn't have, right? C# doesn't have, F# doesn't have. They don't have it, even though they call themselves functional languages. They can't do this, okay? Only Haskell can do this. And, no, there's some, okay, ML can do this. Okay? ML can do it, right? And Scheme. Okay, right. So there are some good guys, right? But the thing is that in C++, it's theoretically possible to do this. It wouldn't be really, really hard. And this is one of the things that you should be like really shouting loud to this standards committee. This is something that would make C++ a usable functional language. Okay? Because in Scala, for instance, they are really struggling. They are doing the trampolining, right? Which is extremely expensive because they don't have arbitrary tail call optimization. But this is because they are working on top of the Java runtime, which does not do it, right? And C++ does not have to work on some runtime. C++ has its own runtime, and C++ could do this. This is not arbitrarily hard, and it would be one feature that would really transform the language. Not all these little additions to the library, you know, tiny little tweaks here and there. This would be a revolutionary thing. Okay? So I want you to, yes, time is over. Yes, I'm done. Okay. And if, one question only. Better be good. One person, okay. Should I pass the?
Can you speak?
Oh, I can speak to this.
Which one?
Here. Oh. Okay, Michael. Shoot.
You knew I was going to ask because you talked about STM.
Right.
We don't have this yet in the software transactional memory spec. No. We are talking about similar things, delaying until the completion of the transaction to issue this. We have various words for those things.
Uh-huh.
I like this. Is there any chance you could submit this, or would you need help to proxy it so that one of us could submit it with you?
This is open source, you know, like anybody wants to submit it, please go ahead. I don't know how to deal with the standards committee. but yeah, feel free.
So from what I see, there's obviously some things we still have to work on. But I think the essence of the details are there. Mm-hmm. Does it require any change to the bind at all, existing bind, or is it?
I think that the name bind means probably something else, right?
Right.
This is just what I call it because.
Oh, okay. So this is not the standard bind.
That's not the same bind. No,
okay.
No.
That's what confused me.
This is the monadic bind.
Okay.
You know, you could call it M bind.
All right. Okay.
Or use the operator. Actually, in Haskell, it's operator greater, equal, which is also overloadable in Haskell. I mean, in C++, right?
Yeah.
So you could use that.
Maybe that's a better one
Maybe
than bind, because
that's
bind really surprised.
Yeah.
That bind really confused a lot of people.
Yeah.
I suspect.
But if you can combine this with coroutines, wow, that would be amazing.
I think that's the key, is to try to push it through and make it part of coroutines, and then we can now use it in STM as well too. Thank you for doing this. Yeah.
Thanks.
I snuck 3 questions in there.
Do we have time for another question? 3 questions. 3 quick questions. Sure.
This is more of a comment to address that point that was just made, since this is getting recorded. Andrei Flinsky wrote a paper on what's called monadic reflection, which sort of describes, if you know how to capture continuations, how to embed arbitrary monads as straight line code. And so there's a direct analog to how to embed this to coroutines. It's actually very well studied. We can talk about that offline sometime.
All right. Thank you.